Great. So hi, and welcome to the three-part lecture series on Stockholm's geology. First part will be on the lithologies of Stockholm. The second part will discuss metamorphism, sulfide rocks, sulfide-bearing rocks, and ductile deformation. And then the third installment will be brittle deformation and brittle structures. Before we get started, I just want to make a advertisement for another SGF advantage, let's say, as a member, is the course that I have. It's an online digital course in engineering geology. If you're just starting out in engineering geology, you just got hired by a geotechnical engineering firm or in any other kind of geotechnical role and need to brush up on your engineering geology or just learn it, I strongly recommend this course. You see the cost there. It's an 18-hour course, so you get to see me for at least 13, 14 hours talking. There's tests between each chapter before you go further. Feel free to investigate it. There's the web, the address there. You should be able to Google it and find it. But let's get going. Let's see, I just got to change one thing. Great. So now, before we start talking about the geology of Stockholm, I thought it would be worth going over a very fast review of the Baltic Shield, or the Finnish-Scandinavian Shield, as it's sometimes called. And we start up in the northeast corner of the Baltic Shield, where we have the Archean area here. The yellow stuff you see here is tonalites and granites, 2.6 to 2.9 billion years old. They were then split up. So that's the continental core. Then they got split up along. Here's a failed arm here, in this green area, a greenstone belt around there, similar to the East African Rift, let's call it. And then on the southwestern side, it split all the way away. We have no idea what the other bit of this Archean continent was or where it is now. We can guess that it's maybe in Greenland. But anyway, it split up, and we have an ocean on this side. That split happened at around 2 billion years ago. So that's the age of these greenstones. And then we developed this big ocean, and we have several island arcs. We have the Skellefteå arc, the Bothnian, the Bergslagen arc. These are like Japanese, think of Japan, like island arcs in an oceanic setting. And you have this big ocean. The blue stuff, the blue rocks here are the oceanic sedimentary basins. The beigeish rocks here are the magmas underneath the volcanic islands. And there's even volcanics here too, but they're just not shown. At around, and this basically developed between 1.9 and 1.8 billion years ago. At around 1.8 billion years, you had a little influx of granites up in the north. They're called the Lena granites, these pink areas down in the south, for instance, the Stockholm granite, which I'll talk about more. And all of this is happening while these arcs develop. They all get slammed back into the continent, also at around between 1.9 and 1.8, probably around 1.85 billion years ago. And we have this all glued together. We have continental growth, a much bigger continent here, and then we have this new continental margin that's more north-south here in the current orientation, and it is now a continental margin that we have subduction coming of the oceanic plate from the west down over and under to the east. Just think Andes, exactly like the Andes. And this is at around 1.7, 1.8, 1.7 billion years old, and this is what's created the Trans-Scandinavian igneous belt. This is what you see in darker pink. And then after between 1.7 and around 1.0 billion years old, we have the Gothian origin, which is mostly a lot of reworking and deformation. And then at around 1.1, we have at around 1.1, we then have another collision and the second Norwegian origin. This is North America coming in from the west, and Greenland and other things. And then we split again, and then we form a new ocean, and then North America comes slamming in again, and we form the Caledonides. in the Paleozoic. So that's the whole history in a very, that's your whole course perhaps, in a very quick summary. But let's get down to the part that's more interesting, where most of the Stockholm rocks are formed, and that's the Speckefini. And this just gives you a nice idea of what that kind of looked like. I want you to imagine it sort of in your head. It always helps me when I think about geology. And here's that continental margin, and here we have these volcanic arcs and back arcs, just like in Japan. And at the time, the paleo setting of Baltic Shield, or of Sweden at that time, was fairly tropical. So the rocks you stand on, or that this building is built on, were built underneath a tropical environment, probably, or subtropical, or something like that. Warmer than it is now. In more detail, you can see that what we have here is we have our oceanic basin here. Here's a margin here, continental margin, and then we have some oceanic basin with the sediments here in blue, and we have various volcanoes or volcanic calderas forming and putting out these more felsic to intermediate volcanics in yellow, and then the magmas underneath in brown here. And the reason why I have this picture is so that you see these colors correspond to the colors you see on a typical SGU map. And so that's what it looked like 1.8 to 1.9 billion years ago. And then, of course, ever since then, all that's been eroded away. And so you're left with this surface. And that's why you see mixtures of blue, kind of beigeish, pinkish granites, and every once in a while some slivers of the volcanics in yellow. So let's look back. That's the sort of framework, regional framework. Let's go and zoom in on Stockholm down there. So here's a map of the greater Stockholm area. And I'm just going to quickly name the units from youngest to oldest. From oldest to youngest. The oldest stuff is the sedimentary basin in blue, and you see that dominates the southern half of Stockholm. Then you have, and that sedimentary gneiss is probably 1.9 billion years old-ish. Around 1.88, let's say, to 1.88 billion years, we have the granitic gneiss and amphibolite intruding in. That's this brown rocks here. You see they're often associated with each other. And then much later, at a 1.8 GA, we have the Stockholm granite, which here is usually shown in this pink color. You see that the granitic gneiss and the Stockholm granite dominate more on the northern side of Stockholm. Then we have later pegmatites and diabases, which the pegmatites are rarely big enough to show at this scale on the map. The diabase is, you see these blue stripes. We'll look at them later in more detail. So let's look at these individual lithologies in detail. And we'll go from oldest to youngest. And by far, to me, the most interesting and the most dominant lithologies on the maps, at least in Stockholm, is the sedimentary gneiss. And I'm trying to give you, of all these lithologies, I'll give you a view of what it looks like on outcrop, in a tunnel, or a road cut, or blasted rock, let's call it, and in geocore, because you will work with all of these if you work in Stockholm. We'll start in the outcrop form, and in the sedimentary gneiss it's not exactly a classical, what you would call turbidite, but it basically consists of alternating layers of more pelitic or originally clay-rich, mica-rich rocks, like you have here, and more samitic or more sandy or silty rocks, which you see here. And then it's then melted, and you have melt veins all through it. And I'll show those. I'll talk about that melting much later. Fairly easy to see the distinctions here on the outcrop. Harder to see it in the tunnel quite often because of lighting. And in geocore, you usually can identify it fairly well. You see it here, the darker, more biotite-rich layers. You see these melt layers, which are marked with the B here, and even D. Some of the characteristics, the sort of identifying characteristics of this is the primary compositional layering that has different grain sizes and different biotite contents. This layer is often very wavy. And I even have some examples here that I'll pass around. And I'll just skip over to the camera here so you see it more clearly. In here. So here's a nice drill core of that. And what you have here is more sandy layers and more biotite rich layers up top here. And a melt vein here. Just pass that around. And a typical identifying feature here also, in this one, you see how wavy the layering is and how it's folded. And down in here, the lighting's not fantastic, but there you see a nice red garnet. Garnet's a dead giveaway of sedimentary because you have more aluminum. Of course, garnets also have a bit of iron in them. So that's the sediments to show right now. Go back to this. Just another detailed view here from a borrowed picture. Just to show you, again, the focus on the more argillitic clay-rich layers. They often can contain sulfides and graphite. These coarser-grained, more quartz feldspar-rich arenite layers. Sometimes you get little strings of amphibolite in here, or it could also be melanosome residuum, which I will talk about later, or the migmatites. And these leucosome veins that cut, which are melt. And again, a reminder of the sort of telltale signs that you're in sedimentary gneiss. It's wavy. You have the alternating compositional layering and different grain size. You have the melt veins, high biotite garnet, biotite content garnets, and pyrite. If you want to look at this stuff yourself here at the university, you can just go, here we are, you can just go over there, and there's a nice little tiny outcrop of it here that shows very typical way of outcropping of it, where you have fractures often along the sedimentary layering, the original sedimentary layering, and they're often rusty. Next rock type is amphibolite. And the way I try to tell people to identify this is think salt and pepper with extra pepper. And you see a rock that's kind of this dark. And I guess easiest to see that texture here in my ring there. Another way to identify it is that it never has a large amount of melt in it. The amount of melt fraction in it, these little white leucosomes, are patchy at best. So if you see a gneiss that has very little melt in it, then it's most likely and it's dark, it's most likely an amphibolite. However, it can contain garnet, so that can trick you a little bit. Here's just an outcrop picture. Here it is when it's more coarse grained, and here is a cut near the university, down near the Oko Kuota, there on the main road, the E18 or E20 road. Here's a nice example with the leucosome vein cutting through, and here's another. And this outcrop here is from on Brunnsviken at the beach, where you can see all kinds of different aspects of the sedimentary gneiss. You can see the pilitic layers here and the wavy banding. You see some little rustitic, more sandy layers. And then you see the leucosome karst cutting it, and this here amphibolite, which often, in this particular case, amphibolite, or in most places in Stockholm, amphibolite can form budens. And doesn't really show very well in this picture, but in drill core, it's basically just very dark, and again, think salt and pepper. The next rock type is granitic gneiss. And there's the more detailed age of it here. Yeah, 1.92 to 1.87 GA. if the difference between it and the sedimentary gneiss is that it's more of a straight gneiss. You see here the foliation is quite straight on it. It's more homogeneous. We don't have a big variation in grain size across this or composition. It's generally coarser grained. And generally speaking, it has lower biotite content. Here's just another picture of it. See how straight it is? This has a bit more biotite in it. And if we go again, I have a few examples, or I have an example. You know what? I'll show them in a minute afterwards, because there's two types of granitic gneiss, and I'll show that. It's important to note that the granitic, what's called granitic gneiss here in Stockholm, actually has a fairly large compositional range. It goes all the way from sort of a tonolitic composition to a monzodiorite to a diorite to almost gabbro. In other words, it goes basically from tonalite to amphibolite. And you can see that in a picture like this here. You can see that this is quite dark here, but there are lighter variations over here, and I'll show more pictures of there. Again, the granitic gneiss is usually coarser grain. You see here that if this was a sediment, these would be some mighty big feldspar grains and quartz grains. These would be pebbly almost, and these aren't pebbles. These are metamorphically recrystallized anyway. This is often called mapped as sediment, as granitic gneiss as well, something like this, but I'll later on suggest that maybe this is sedimentary gneiss. I'll tell you why later. But since this is a gneiss that is still, let's say, stripy, and contains biotite, quartz, and feldspars, the same mineral constituents, it can be quite difficult to distinguish it from sedimentary gneiss. And here's a good, especially when you're in geocore, for instance. And here's a good example of that. And here at the top is granitic gneiss, what I would interpret as granitic gneiss. And these veins are probably not so much melt veins. Some might be melt veins, but they're probably just pegmatites intruding in along foliation and being disaggregated. Whereas on the bottom, this is sedimentary gneiss. Often the granitic gneiss is more pink. If you have leucocratic veins, they're pink. And the sedimentary gneiss, they're white. But one of the distinguishing characteristics here still is you see there is a much more variation in grain size here if you ignore the lighter colored layers here. And you can even start to see things like, you know, graded bedding if you have a good imagination here. But even at the tunnel scale, it can sometimes be difficult. This, for instance, is the place in a tunnel I've been in, and I couldn't decide whether this was granitic or sedimentary gneiss. Now, there's another variety of granitic gneiss on the Stockholm that's shown with these white dots on the Stockholm geology maps, or the SGU maps. And I'll show you a picture of that. And it's much easier to distinguish from sedimentary gneiss. And I'll just show you some pictures of some samples from these 4 quarries. And you see it's all fairly similar. It can be either not so foliated or strongly foliated. It in fact has an LS fabric, which I'll show in a minute. It has various amounts of mica and amphibole in it. Here you can see a very leucocratic variant. In geocore, it looks like this. See, it's quite a bit more homogeneous in its grain size. And you have some little, possibly some in situ or in-source melt leucosomes here, which I'll talk about later. Here it is, the same geocore, but you can see somehow that you can see that it can progressively change its amount of quartz and biotite and feldspar amounts. Here it gets progressively a little bit lighter as you go to here, especially over here. Here you have maybe more strain, a little more grain size. And this kind of, so just to help you visualize what geocore might look like at outcrop scale, this is what the outcrop of that would probably look like. And I'll just go back again to the camera and show you the 2 different varieties of granitic gneiss I was talking about here. Here is the one that has these kind of a pink veins in it. Looks like that. Pass that around. And here is the what's called porphyritic one, the one with white dots, and that has this LS fabric. And here you see, you know, it looks basically on this side, you might just call it a granite. But on this side, you can see that it has quite a strong fabric in it, which you might want to call foliation. But if you, we know from structural geology that the fact that we have almost no fabric on this face, but a stretched out fabric on this face means that we have a lineation in this rock. You can still see that it has a foliation as well in it, but the lineation is perhaps stronger than the foliation. So this would be a LS fabric. And this is very common for this rock in Stockholm. And the lineation is usually fairly steep. So all of these old rocks together usually are interfingered with one another and can make quite complex geology to interpret. And what they form what you could call a composite gneiss. So if you're out mapping and they're just all mixed together, it's okay to make a map unit called composite gneiss and just say what its constituents are. Components, perhaps, right word there. Here we have a sedimentary gneiss as the base one. Here's the more sandy layers. These layers are the more clay layers, and then we have these leucosomes or diatexitic veins coming in over here, and then we have a nice amphibolite boudin again. Same thing here. We have this amphibolite here. We have the sedimentary gneiss, and then we have the Stockholm granite that cuts right across it, which I'm going to show you next, the Stockholm granite in detail. Again, in tunnels, it's not nearly as easy. I can at least identify that this is an amphibolite up here because it doesn't have enough melt veins. It's very dark and it doesn't have enough melt veins in it. What's going on here is a whole nother story and not so easy to interpret. Then we come to the youngest rock type. See if I can get that disappear. There we go. To the youngest rock type, which is Stockholm granite. Now, Stockholm granite is classically considered incredibly boring for a geologically boring rock. This is what it's normally characterized as, or normally described as an equigranular gray granite. This is what it looks like in outcrop. This is what it looks like in a drill core. But it can get altered, and then it becomes more red here. Let's see this pink alteration. And if it gets strongly altered, you can get weakness zones and chlorite-filled crush zones like you see down here. And there's even a variety of it, an altered variety of it called epicyanite, which you see down here. You see all the little holes. It's porous, where the quartz has been removed. The Stockholm granite, as you see here, has got no foliation in it most of the time, only in very late, very localized ductile deformation zones will you see it deformed. Otherwise, no foliation, generally speaking. It almost always cross-cuts all the older gneisses, because remember, this is 1.8 GA. It's almost 100 million years younger. And it's massive, I said. And as you notice, there's not much biotite in it. There are more biotite-rich varieties, but they're not as common. Now, it's previously been described, and it is, up till now, SGU and still, they describe the Stockholm granite as there's two varieties. There's a porphyritic variety, which is the Vallentuna granite up on the north side of Stockholm, and they even have a little white dots on it. And it's pink, and then there's this boring gray one. But I've been in a particular tunnel. I've seen probably 7 different generations of it, and with different textures, which is a new kind of thing. And I'll show you some of those pictures that prove it. we know that the granite came in after anatexis. Anatexis means melting. After the melting, because we see here the sedimentary gneiss. Here's a melt vein here, and we see the granite just cutting right across it. Here's again the sedimentary gneiss with some melt veins, or sedimentary gneiss with melt veins going across it, and you just see this completely isolated as xenoliths. You can see obvious several generations, and these margins are quite cold and chilled. You can see here. Here's a lighter colored variant that is older and being cut by a darker colored variant of Stockholm granite. Same thing again. Here's the older granite being cut by the younger. Here it is dry and wet. You see little xenoliths of the younger and the older. Again, more examples here. Here's a porphyritic variety, and then a darker non-porphyritic, either an offshoot or a separate generation. Here's a other type of porphyritic variety where the phenocryst or the matrix is very fine grained. Here's a very leucocratic variety here. And here's a good example of them cross-cutting each other. Here's the normal one that I showed in the first picture that most people think of as Stockholm granite, being cut by a lighter variety, then being cut by a much darker variety. And this is one of my favorite pictures of this. So it's showing, again, the same three generations, basically. And you see that they must be at least enough difference in age for them to chill. Again, the older, boring or gray variety, very leucocratic variety, and then a very mafic, a more mafic variety. And you don't have to go in that special tunnel to see this. You can actually just go to Bergshamra here on E18 and pull off and look over the E18 at this nice outcrop here, where you see the sedimentary gneisses. You see the Stockholm granite cross-cutting it, this gray variety, the older variety, and then you see some of these lighter colored, younger variety cutting straight across it. What's interesting here is we have no idea if these are even the same age. Maybe the only thing that should be called Stockholm granite is this gray stuff. These other ones could be much younger. We have no idea. It is a future project I hope to get funded. This granite also comes in during the brittle deformation. You see here a vein, pegmatite vein, being slightly deformed or faulted here, and then you have this darker gray granite coming in. Talk a little bit about the alteration of the granite and how it looks. Here is just a series of pictures in a tunnel, seeing the progressive alteration of the granite. We start in fresh, starts to get a little bit pink. You can sometimes see where this hematite alteration is coming in along veins, possibly, or along fractures, microfractures. Here you see those more clearly, and as we keep on progressing, we basically come to a red granite at the end. And then you start getting even later fracture fills, which I'll talk about in the third lecture. And I'm going to hark on this much more on the last lecture, but a typical feature of the Stockholm granite, even the fresh Stockholm granite, is that you get very flat subhorizontal fractures in it quite often, and they often are fairly leaky, transmissive. Then what is commonly considered, let's say, another younger variety of lithology in Stockholm is pegmatite. But in fact, I'll probably try to argue here that there's more ages of pegmatite than just one, more generations. But there's pink and white pegmatite in Stockholm. And the white pegmatite is probably diatexite, which I'll talk about later. In drill core, here's a typical pink pegmatite. Oftentimes it's disaggregated and deformed. You can see in this picture here, you see it's broken up in little bits. This middle picture is what I would probably call diatexite. It looks kind of like pegmatite. It's very coarse grained, granitic in composition, but I'll tell you later why I think it's not pegmatite. And here's a decent picture here of a tunnel where you see both pink pegmatite and white pegmatite in the same picture, cutting a amphibolite. There's a few great localities or places that I've seen classic pegmatite zoning, like that textbook zoning. This is a nice example from the Slussen station, bus station that's being built right now, or it's done basically. The rock part is at least. You see there the tunnel here, and then there's another tunnel up here. So this is a bridge across, and a pegmatite just happens to run right in that bridge. And you get classic zoning here. You start with this fine-grained aplite margins. You get the graphic quartz, plagioclase quartz margin next layer in. You get coarse microcline crystals here, and then you have a quartz core. And as I was mentioning before, it's not always the youngest rock, as most people like to think. In this picture, this is the same. That's the same dike here, but just a picture lower down from it. We start with the oldest rock, which is the sedimentary gneiss. Then comes in the pegmatite. You get a little offshoot from the pegmatite coming down here, which is important in a minute, because the Stockholm granite here cross-cuts it. So obviously this pegmatite must be older than the granite. And then you see this little white guy here. It's a little breccia that cuts across all of this. And if I zoom in on that breccia, you can see it's cross-cutting even in there, and it's a proper breccia with a proper brittle type thing. You see little bits of the gneiss inside of it there. The last rock type of lithology I'll talk about is the diabase. These are much younger than anything else. So far, everything I've shown you is probably in the range between 1.8 and 1.9 billion years old. These are 1.26. That's the guess on the age date for them. And as you see, they completely cross-cut everything. They're usually dark gray to black to, in geocore, they even can look a little bit purple. And I'm not going to switch off the camera to show this here, but you can look in the top corner here. In geocore, that you can, the cross-cutting character is also quite apparent in this. And nobody's going to want to touch it now. Yeah, it's completely fine-grained. You can't see any texture. If you're lucky, you might see some little phenocrysts. I'll show that in the next picture. But it's a massive rock, obviously not foliated because it's later. Typically in Stockholm, people assume that these are vertical dikes or subvertical or steeply dipping, but in a lot of the observations I've seen in tunnels, in fact, they're moderately dipping, as you see here. You see a nice little chill margin here that's got its own fracture group in it. And it's obviously gone along some sort of a small little deformation zone here because you have a little bit of offset here with that thing. In drill core, it looks like this. Here's a little, it's dark, homogeneous. It's very easy to spot. When you look up close, you can see some of these little plagioclase phenocrysts here. Sometimes they can be very, very thin dikes that might confuse you. Here we have a breccia in a fault zone. And here's a little bit of diabase dike cutting right across it. That means that this breccia is actually older than the diabase. So there is some sort of a brittle / ductile deformation going on, probably even at the end of the 1.8 GA billion year events. This SGU map shows the diabase dikes. I've tried to highlight them here a little better. You see these, they're generally northwest trending. That's the main trend of them. And according to them, subvertical often. But there are, as I said, other generations or variations that are moderately dipping. So keep it in mind. So that ends the first lecture. We can take a break and a 5 or 10 minute break and come back for the next one.